Let me just introduce him. So the next talk is Andrea Simonetto, and he got his PhD from Delft University of Technology with IBM Research, and he's done very nice work on time-invariant optimization.
Oh, thanks, Stephen. Thanks the organizer to have invited me here in this wonderful place. So I'm gonna continue the line of thought that Florian has set in the previous talk, and this is gonna be the motive of this morning, I'd say, with Emiliano afterwards. So the idea here is to do optimization or control in real time, and I'm focusing on optimization and how to solve optimization problems that are changing in time. And this is joint work with many people, above all Emiliano, over the last 5 years. I will briefly touch upon power systems, but the focus is really optimization. So I set the stage with the fact that how we see now big interconnected system is that at the core of them we see an optimization problem, and I put it in this way. I say I want to minimize a certain cost function, and x, this yellow x, will be my decision variable. Those can be powers, voltages, or other things. And then typically you will have some physics constraints, and that can be linear, etc. And then you will have some engineering constraints. Your power has to be limited, your voltages has to be in certain boxes. Okay, so the twist here is that when we are looking at very large scale problems, like say Europe or more, or when you want to solve this optimization problem very fast because you want to dispatch your decision variable very fast at very high frequency, it makes sense that you cannot solve it exactly at every time you need it. So it makes sense to consider optimization problems that are now parameterized over time. Okay, so the idea would be not to solve it exactly, because you cannot. You possibly cannot solve it exactly at every time you need the solution. So, so in this talk, I will look at some nice problems in the sense of convexity, and how we can generate solutions or approximate solutions that eventually tracks the solution trajectory. So you start arbitrarily, you build up some algorithm that eventually tracks the solution trajectory of your optimization problem, while this changes over time. And not only will react to the changes of the optimization problem, say by measuring the wind or the solar, but we actually also proact on those changes by predict how the optimal solution will change from time to time. Now in the next talk by Emiliano, this will be extended somehow to a convexified problem, to more complicated linearizations of AC optimal power flow. Measurements will be included, so that we will use measurement feedback to enforce physics and reduce approximation error. So so that will be covered by Emiliano, and in the previous talk by Florian, he touched upon how control can be embedded, and well, you listen to him, so you know already everything. I don't have to tell you. So here it's really to look back at what Florian has said. Here is really how we drop the argmin, how we don't solve the optimization problem exactly, but use first order methods to track the optimization trajectory and never solve like these continental size problems. So okay, notation first, a little bit of definitions. So we have a very nice smooth convex functions. So why we want to set it in this way? Because if it doesn't work even for nice problems, then forget about it, right? So instead, if we know at least it works for, say, nice convex functions, then we may do some tricks to make it work for more complicated non-convex, non-linear, etc. So here we have a very, say, prototypical problem. You want to minimize the cost. This cost is smooth and convex for all the time t, and the decision variable in some convex set x. And so we want to find the solution trajectory. Now I'm saying that f is m strongly convex uniformly over time. Therefore, the solution trajectory is unique, and which I wrote it here. So, okay, how we go about it is that we use a discrete time approach for many reasons. But what we do is that you sample the problem at time tk. You define a certain sampling period. And so for each case here, you will have problems that are time invariant. So if you have very small problems, or you allow yourself to have a day to solve them, you could say, okay, I solved them exactly, I don't care, fine, everything goes fine. But if you can't do that, and I argue that is increasingly important now, I'm pushing forward a smarter choice, which is using first order method. You start with a certain x0, feasible, but it doesn't have to be, and then you generate a sequence such that eventually the distance with the optimizer trajectory becomes smaller and smaller, and since it's a discrete time algorithm and things changes, you will have an asymptotical error which depends on the sampling period. So depending on your computational resources and how fast you want to go, then you can tune this asymptotical error. And we will look at prediction correction schemes, so something that will predict ahead how the optimizer changes, and then corrects based on the sampling of the cost function or gradient, versus correction only, which only reacts to changes in the cost function. And now the reason for that is that prediction correction offers clear advantages, and in general has even better accuracy at fixed computational time. So if you fix how much computation you want to do for each sampling period, which is kind of limited by your hardware, then in general, or in many cases, even doing prediction instead of continuing doing correction offers as lower asymptotical error, as I'll show you later. So the price to pay is, of course, need for nice behaving functions, although now we are extending into more general framework. Okay, this is a little bit of a background. It's not extremely new. Is rooted in, the initial ideas rooted in Polyak's school of non-stationary optimization or parametric optimization from Robinson, Rockefeller. Here what I really want to show you is some computational lightweight method to tackle these time-varying constraint problems. Okay, so all this to say how we are going to do, how we are going to go about it. So the idea really is to, in this simple example, there are more complicated examples, but is in this simple example, you will have this prototypical problem, which is in the end a constraint optimization problem, and at the core is really rewrite the same problem as first order optimality conditions. Here in terms of generalized equations, because here we have a constraint set. So solving this is basically the same as finding a solution for this generalized equation for all the k's. Okay, so if you start a certain x0 at time tk, we want to predict. So imagine you corrected, you do all the things. Now at time tk, you want to predict ahead the solution at time tk plus 1. And that's going to be xk plus 1 given k. And at time tk plus 1, so at the next time, we would sample the new problem, and then we would correct the prediction that we have, this xk plus 1 given k, with the new data that comes. And how we do prediction, we need a model to do prediction. And how we construct the model, we use first order optimality conditions. So in the end, the prediction would mean solving a generalized equation in the future. Okay, this is indices by time tk plus 1. This is of course not possible at time tk. What do you do? What every engineers do is you do a Taylor expanssions in the future, and you use the gradient at time now. You will use second order information, so that's why I need a nice behaving functions, because I need the Hessian to exist and being well behaving. And then the twist is now that you have also a time derivative of the gradient, which bear with me, you don't have to have it, you can estimate it, it works fine. But okay, let's put it in this way. If you don't like it, put a tilde here, is an estimated, that's fine. And this will be the normal cone of your constraint set in the future. So this now, it's all the constants are actually known at time tk. The only thing that you don't know is this predicted, but then it means solving this generalized equation, which is nothing else rather than a QP problem, a quadratic programming problem. And because this is a constraint, this is a constant, this is a matrix constant, this is enters linearly, and this is also a constant, so it is a quadratic programming. And but you can solve it. So if you have computational resources, or you have a very nice toolbox to solve quadratic programming, you can solve it exactly. Otherwise, you can do p iterations of a projected gradient method. It works beautifully as well. Here, the idea is that you have to compute the gradient, this one, the Hessian, and this derivative of the gradient only once. And then you can run p steps of the gradient on the same data, and then you get this approximate prediction, and this approximate prediction will go to the exact prediction in the way I say, as p, the number of gradient steps, goes to infinity. We don't care, we don't go to infinity, we truncate it at our computational resources, so we will have this approximate one. That's fine. So you are predicting ahead how your optimizer are changing over time based on optimality conditions, or a perturbed version of the optimality conditions. Those are your basically model. So this is very similar to, say, a Kalman filter, where you predict how things change based on the model, which is here the first order optimality condition. And then what you do, you take measurements, and the measurements here is in fact the gradient of the new function. And this is how you do correction. You sample the new problem, in this case just the gradient of the new problem, and then you can do ICC step of the projected gradient. Okay, whenever that is available, you can do that. And I said prediction correction in this sense involves only matrix vector multiplications, so no matrix inversion is needed. And of course you will have to evaluate the Hessian, but if those are easy to compute, that's a very lightweight method. And yeah, this is a very sketch to give you an idea, just if you already did. Okay, so this is in yellow is the cost function. The cost function changes over time. This is in gray is your constraint set. In blue is going to be the solution trajectory. And the idea is that you start somewhere here, you do, you're predicting how things will be in the future, and then when you're here, you're gonna go, you're correcting based on the new cost or new gradient evaluation, and so you're going down, and then eventually you're gonna go closer and closer to your solution trajectory. Okay, so this is the main results, and then we stop the math. We go a little bit more on examples. So take F to be M strongly smooth and L strongly convex. Actually, it's the other way around. M strongly convex and L strongly smooth. Then you have a bound on how the gradient changes on it over time. Then by selecting this alpha and beta, which were the step size of the gradient in the predicted and in the correction phase, smaller than a certain constant, 2 divided by L. This is not very different from what Florian has said, in fact, right? So he had a similar condition on the step size, and that's related to timescale separations in some sense. So that's what you have. If you select alpha and beta small, then there is a minimal number of correction steps for which globally, so starting anywhere, you can converge to a ball around the optimizer trajectory and a ball that depends on the sampling period and on the number of correction steps that you allow yourself to take. And this is actually less than 1, so this is going to go smaller and smaller if C is bigger and bigger. Okay, so there is a natural trade-off here between sampling period and number of correction steps. And of course, sampling period and correction step will have to be chosen appropriately based on your hardware and what you want to achieve. And this is very general, so the first result is very general. It just say you need a bound on how the gradient changes. So you need a bound on how the problem changes over time. If it changes dramatically, then forget about it. But if it changes reasonably, then actually you have a result of the sort. The result is also parameterized on the bound that you have here. So it would work even if it changes dramatically, but then the result is a little bit meaningless because it says that the asymptotical error is just blows up. Okay, but what you have here, this is the extra part. This is the extra bit that comes from having a prediction part. It says that you have, if now you have also bounded higher derivatives, so meaning third order derivatives and yes, mixed derivatives, then locally, what you have locally is that now your error decreases because you have a term that depends quadratically with the sampling period, and the sampling period is typically small, so this is smaller than this guy, and a term that depends linearly on the sampling period, but you have now the prediction. So this part over here is actually the error that comes from a finite prediction steps. So if you could solve the quadratic programming exactly, this term would go away, but if you don't, that's fine. You will have a term that depends on how many prediction steps you are going to do. And again, this gives you a trade-off between how you want to be accurate and how you want to spend in terms of computational resources. So this is the main results. You can extend this, and work has been done both in the continuous settings, and there is a lot of work in that sense. Florian, although he look at different things, but it is a continuous setting in the sense. You can have linear constraint problems, and in that sense you would do dual decomposition. You can extend that in the dual decomposition framework as well. You would have prediction of the dual variables and then correction of them thereof. We are working on more complicated cost functions, which are sums of very nicely behaving functions, and some nasty G's, which could be the indicator functions or others, via some splitting methods, and that seems to work fine as well. So the framework of prediction correction seems to carry over more complicated classes of optimization problems. And of course, I'm not touching upon here, but there is a large literature in the case of correction-only methods. But I'm just pointing you to the relevant literature. So, okay, let's stop for a moment on the math. Let's look at what this means for power systems. Okay, so again, this is joint work with many other people. I'm more in the optimization perspective, but they assure me that this is right from the power system perspective. So if it's not, then I'm going to ask Emiliano about it. So I'm going to show you two examples. The first example is more nicely behaving. The second example is nastier. And I'm gonna set up my models. I'm going to give you the equations, and then I'm going to argue that prediction correction works better than, say, correction only or naive approaches, even when the computational time is fixed for each sampling period, and even if you don't have the gradient, the time derivative of the gradient. So if you approximate that with the previous, with some backward finite difference approximation. So the first example, it's about optimizing the operation of this DIR, and the idea would be to, you would have those DIR connected to a power distribution system, and you want to optimize the operation in real time, which means we were going to give set points, and those are going to be updated every second or even sub-second at time scales. Okay, so you will have one slack bus and nodes with controllable DRL. Yes, notation, we will get some injected complex power, so we are looking at AC power flow here. You're going to have the active power flow at the point of connection with the rest of the grid, this P0. We packed the decision variables, so the decision variables are actually these complex powers. Here, in one, you stack it in a vector, that's standard. Here, for this particular example, we have an approximate linear relationship between x's, this power, and P0 in this way. Okay, it's a linear relationship. We know that is not the case in reality, but it seems to work very well in the other problems we are looking at. Okay, so those are models. So this M and eta are models parameters. So, okay, and what is the problem in the end that we want to solve? It's a set point, so you want to track in real time these set points. So this will be penalizing the fact that you are not at the set point. This is actually a cost function for each node of the buses that say they probably, so those are customers that are trying to maximizing or minimizing a given performance objective. And then there is a trade-off between what the grid tells you to do and what you want to do. And of course, this decision variable are in some set. You cannot do exactly anything you want. You have to stay inside some boxes. And everything now depends on these x's. And these are my decision variable that scales as 2n, where n is the number of, this should be big N, number of buses. Okay, so this C, I am allowed to design it as I want, so then I design it quadratically, so this is now a very nice quadratic problem, because this is linear in X, so this is a quadratic problem that I can solve with my method, this is what we did. We used some real data belonging to residential load from Sacramento metro area. 1 second granularity, we tested on a 37 node test feeder with a single phase. So this is how, if you look at this white part, this is actually how fast the non-controllable loads are changing, and this is, if you don't read it very well, this is from noon to 1, so this is pretty fast. Those are oscillating, and we want to we want to set, we are given a set point which is instead slowly changing. Okay, so right, this is just okay. So what we really show here is that if we run our method with say, okay, with 3 prediction steps and 1 correction steps, and we tune a correction only, so a method that uses only the new information but does not predict how the optimizer changes over time, which means p equal to 0, but in this case we tune it in a way that the computational time that you spend doing this is the same as the computational time you spend doing this. Okay, so C in this case is equal to 3. Then what we show here is that if you look at the tracking error, so the difference between this xk minus x star at tk, then what you observe is that even at the fixed computational time, your prediction correction is doing better than correction only alone. So what I'm saying is that you have enough, you have information about how your optimizer changes over time. Use it. Even though it seems that you are doing extra computations, it doesn't matter. In fact, you are doing better to stop your prediction steps, start correcting, and in the end, the asymptotical error is better in this case by 25%. Okay, this is a very simplified toy example. How this would work in a more complicated example. This is the goal of the second thing that I'm going to show you. It's related to distribution state estimation. So you have a grid. You want to collect the measurements from PMUs. You want to collect measurement for smart meters. Again, is in real time, at least for PMUs, which means the time scale is going to be of seconds. You probably want to collect different measurement at different time scales. That's fine. And the idea is that, so we put a setting, we have a multi-phase unbalanced distribution systems with Y and delta connected loads, so it's more complicated than the one before. But in fact, it's very similar in ideology. You will pack your decision variables, so you will pack your voltages, you will pack your power in vectors. Again, as before, we use an approximate linear relationship between voltages and powers here as a linearized AC model, and then we need an equation for the measurements you get. So you will collect the measurements at time tk in a vector, and that's depend linearly because of this relationship on the powers, and those are problem parameters. This is the noise that enters in the system, and this can be anything really. It can be PMUs, it can be smart meters, it can be something else that you have about in your grid. We don't care at this moment, as long as we have this nice linear relationship. Now, the difference, the twist that we have with the previous examples that I gave you is that we have a cost function that in fact has a Uber term here. And why I put a Uber term here is that maybe some of the measurements are not very accurate and you want to robustify your estimator. Okay, that's fine. What people do is to put a Uber function here, which is basically say that that you're robustifying, but you're losing differentiability. Okay, you're losing differentiability of the derivative, which means that your third derivative of your cost function do not exist. So the second part of the theorem I show you do not apply, but the first part does. So we wonder, okay, does still the same result would still hold in the sense that the prediction correction would still outperform the correction or not at the given computational time, even in this more complicated setting or more taxing setting. So here we have we add a regularizer over here. We can talk about this detail later. That's not very important at this moment. The very important thing is that we have a Uber function and then destroys the nice properties of this quadratic function over here, and we want to see whether we still regain the same computational results. So we tested on real data. This is come from somewhere else. 6 seconds of granularity. We tested on 37 node test feeder and also on 123, although I'm only showing the 37 results here for in the interest of time. And this is 5 examples of different power trajectory. So you see that how they are fluctuating. This is just to show that I'm not taking just constant and pretending that I'm looking at time varying things. Okay, so again, same setting or similar setting. We choose our P's and C's, which is the number of prediction steps and correction steps, in a ways that the computational time for a correction only, so a naive approach, will be the same as a more complex, more intelligent, I'd say, or predictive approach. Okay, so here, by the time you do 3 correction steps, you actually can do 8 prediction steps. And why is that so? Because the correction steps has to evaluate the gradient at the new step, at the new point, while the prediction steps, once he has the time derivative of the gradient and the Hessian, the only thing it does is iterating on that, so matrix vector multiplication. So besides a fixed cost, the prediction steps are cheaper than running correction. So that's the idea. So we remind the asymptotical error. The asymptotical error depends on, in this particular case, because we don't have a nice behaving function, will depend linearly on the sampling period. So the smaller the sampling period, the asymptotical error will decrease. It will depend on C0, and C0 is actually the bound on how the gradient varies over time. So the greater it is, this will blow up. The smaller it is, will be smaller, of course. And then it depends on functions parameter. So this is the conditioning of the function. And then it depends on this contraction parameter and exponentially on the number of prediction and correction steps. So if this is higher, this goes down, etc. If you have a lot of computational power, then you can make it 0, but then possibly your sampling period is too long, etc. Okay, I guess you got it. So this is one of the figures. This takes x's. So this is a relative error, relative asymptotical error of your power. And in blue, I have the prediction correction scheme, and in yellow here is the correction only. And this is, again, I want to stress this is at the same computational, with the same computational time. So the computational effort is the same, but by carefully deciding how to predict and how to correct or when to do that, then you gain, in this case, even 30% at certain area. So if you look at this graph, what is really what striked out is that you may have fluctuations, fine, and at some point during fluctuations both methods don't work very well, or you have spikes, and that's fine in the way, in a sense, because you didn't expect that to happen. You have fluctuation, that's something that happens, but then you quickly recover, and you actually recover quicker, faster, if you use a predictive model rather than only a corrective model. So we have, you can rephrase it as the prediction correction would be a data-driven methods that is faster than just look what's happening and react to that. Okay, so I'm going to wrap it up with some take-home messages, and then there is plenty of time to do to ask questions. So here I wanted to really push forward a framework, which is this prediction correction. You can use it for power system, you can use it for other things, you can use it every time you have an optimization problem that you cannot solve exactly at the time frame you want to dispatch your decisions. And I wanted to say that this works well even at fixed computational time, even if the time derivative of the gradient is unknown. That's fine, you can estimate it. And even if the function is not that nice, although I didn't touch on this very much, but okay, it can be extended even if the function is not that nice. I show you some examples so that prediction correction can be applied also to realistic settings of with this linearized AC power flow equations with encouraging results. Okay. A lot of things are still to be done in that direction, and especially to test scalability, parametric tuning, looking at more complicated problems, looking at non-convex problems, and I think in that, looking forward, what would be very interesting to do is to put together these ideas with Florian's ideas and Emiliano's feedback of measurements that we would linearize the AC power flow equations possibly, and then you could to correct for mistakes that you make here. Okay, but I'll let Emiliano talk about that later, and with this I'd like to thank you and take questions. Yeah. Yes.
Distributed state estimation, when you go to the non-convex case that you mentioned you're looking at, so AC power flow, first order methods are really slow and bad. And I mean, it's not by chance that we always use Newton method to solve state estimation. Of course, here you have PMU, so things are linear, but do you have any thoughts about using second order machinery instead of first order, given that they're really slow?
Yes, yes. Well, that depends on your computational resources that you have. So if you have, or sampling periods that you allow yourself to have. So if you have a little bit more, you could imagine that you could solve the prediction exactly. That's a QP, and you could use second order methods to solve that. You could do just one shot of it, so the prediction would be exact. And then the correction part, you could use second order methods as well. It's a convex, in that case, it's a convex optimization problem. You could use interior point methods even, but you have to truncate. I mean, it really depends if you can allow that, right? So if you have enough time, then you could. But if you don't, maybe if you have a continental size network and you cannot even invert a matrix, then there is of course a trade-off. Right? So I'd say how we see it implemented is probably that if you have a very big network, you probably already know more or less, and then things changes, but they don't change dramatically in the sampling period that you're looking at, right? So even first order method would work fine because you're already around.
But then at that point you will really gain out of using the second order method.
You're right. I mean, if you can afford that, yeah. But I mean, you could think you could do that. Yeah. Yes.
So in the prediction step, you need to estimate how the problem is changing with time, right?
That is correct.
And you said you approximate the gradient. How do you approximate? By finite difference?
Finite, yes. Yes, with very naive would be to have a finite difference in the backward finite difference. Of course, that would depend on the noise that you have, right? So if it's very noisy, there is no. But if it changes smoothly, then that's fine.
Yeah. I think if you write then out the overall gradient step with the finite difference approximation, this will probably be a discrete time PD control.
Absolutely, absolutely. That's actually the same. That's exactly what you have. Yes, because the P, it's the gradient.
Yes.
It's proportional to the gradient, so it's the P, and the D is you're in fact looking at the derivative, so it's a PD controller. I've tried to have the integral control there, but I haven't been able to prove stability in that sense because then would put the error to 0, right? So if you had integral control, but I couldn't figure out. But you can. Yes.
On the prediction, do you have some prediction for the wind or solar or the topology or things like that, or just
nothing?
Nothing.
Nothing.
Okay. So the topology, you believe that the topology is the same for the grid, for example. You have some switching between prediction and correction. What happened?
So, what is that? Let's see. Okay, let's look at this. Here I'm interested in optimization problem that changes over time. And the idea here is to predict how they change over time by how this gradient changes over time. Of course, in that sense, I'm learning how wind is changing. I'm learning how solar is changing, and I'm incorporating that inside here, right? Provided that this C0, which means the norm of this guy is small enough, then I'm fine. If you are looking at more drastic thing, like changing a line or changing topology, that this could be huge, right? Because so in that sense, that's something that we haven't looked at. But there is a lot of so the thing that we are advocating here, and in different ways from me, Florian, and Emiliano, is that we should look at optimization problem in a more systematic and control theoretic way, where you can incorporate dynamics inside. And it's true what you're saying, that there could be dramatic changes that could break this down. That's fine, but there are tools in the system theory, like hybrid systems, that could be, or switching systems, right, that you could use to tackle this thing. We haven't done it. I'm just saying in the future this could be taken in.
Because we spend a lot of time studying Kalman filter, for example.
Absolutely.
Yes, and in the end we were stuck by this topology problem. So because then we don't know how to predict that. So it was we stopped. Even in simulation, yes. So we never go to any kind of experimentation.
That's. I mean, it's. I don't think anybody could say how to predict things that they.
Yeah, of course. I understand that, but
I mean, more interesting if you know how they change it, because it's you that control it. That's much more interesting. The other one would be robustifying the problem to changes. And as Stephen has said, if that happens once and then everything goes as fine, then that's okay. I mean, in this convex setting, somehow you're going off, but then you're gonna get together, right? As long as these dramatic changes do not happen often enough to destroy everything, then stability or convergence is still guaranteed. But it's a very nice question. Yes?
Following up on his question, so the way you do the prediction by taking a finite difference step in the past,
yes,
it's probably exact for a system that has only one state, 1 degree of freedom.
Mm-hmm.
Now think about taking 10 steps in the past, you can probably predict a 10th order system. So essentially building an observer there.
Sure, of course, yes. Yeah, in a way,
Did you
yes.
exploit that idea?
No, I haven't explored that. There are certain things, I mean, there is an obvious trade-off between how much computation you put inside and how much you want to. So it's a very fine line in saying prediction is actually more convenient than do correction, right? Because in a system where you don't know anything and your predictions are all wrong, then you just do a lot of corrections. so that's, but of course.
I have a question. So can your framework extend to the case where the feasible set also changes over time?
I mean, in that depends. There is no straight answer to that. So in this case, I don't. The feasible set do not changes over time. In some cases, for other problems, we are allowed to have a set that changes over time. But as far as I remember, and I think in the prediction correction, the set do not changes over time. While in correction schemes, you can allow that to change over time. But then something very interesting happens is that your point, your axis, has to be feasible not only with respect to your current set, but also in the past. So there is like a backward feasibility. But it's something interesting that happens there. I couldn't extend it to this setting, specifically because this is technically a normal cone operator, and I want to get rid of it to have a nice analysis. So that's So if it changes over time, that doesn't cancel out. That's
I guess you need a model on how xt, the feasible set capital xt changes.
yes, yes, yeah. But we did some work on primal dual, and then we get the model based on the dual variables, but not here.
Any other questions? So, following up on the second order question, second order method question. So, if you do the second order method, either on the say on the correction side, one thing that we find is that it, not surprisingly, converges faster than, or it tracks better.
Mm-hmm.
On the other hand, one thing that becomes more challenging than if you just do the first order is that the constraints are more complicated. That let's say you have non-convex inequality constraints, or convex non-convex inequality or equality constraints. Then the second order method becomes it becomes harder. I don't know whether you have explored some. Not in discrete setting. I've seen some work in continuous settings from Ribeir's group that do interior point method, precision correction interior point method applied to different constraint set. So in that sense, it's a second order method. It's a continuous setting. So that's you will need well, you will have to be very fast. So it's pros and cons, but yeah. Not here, not here yet. So, can you comment a little bit more? You talked a little bit about that at the beginning, the connection of this with Florence. There's certainly a lot of interesting connections.
Yeah, so there are, I think there are a lot of connections. So one of the connections is the idea to use first order methods, or methods that get rid of the argument. And why is that? Is that possibly because in very big systems you cannot solve the problem exactly, or because you want very high frequency control. The thing that I have here that is that my variables, the changes are exogenous. Right? So this TK is exogenous, which means that I observe the changes, but I don't make the changes. When you look at control more and you put together control and optimization, and especially say model predicted control, what happens really is that you take a decision by solving, you take an approximate decision by solving a prediction correction, for instance, and then the approximate decision will enter in how you define the next problem, right? So this is a more control theoretic way to solve it. So I think Florian has a way to do it, at least an idea to do it into in a continuous setting, because he has explicitly the dynamical system there, and see how those things plays out. There is a lot of research in that direction as well. And then what I wanted to say, yeah, so the difference between our work is that this is discrete and is really taking care of, okay, how much computational power you allow and the trade-off between what you can do and what you have at the end, asymptotical error, while he's more continuous setting. But I think there are a lot of parallelism and things. I mean, you obviously do projection over this very complicated manifold. We don't. But yeah, so lots of research that could be continued in that direction.
So maybe the connection with Emiliano's talk will be stronger where you close the loop.
Yeah.
Yes.
Yeah, it just came to my mind. So you go forward in time. You could as well then go backward in time if your goal is just to get a trajectory of solutions rather than getting them in real time. Did you think of it? Does it make sense?
So what do you mean? You want to? So you want the old trajectory, and
Yes.
so you say at time tk I can continue doing calculations of the other one, or?
What I meant is you have a time interval,
Yes.
and you have observations over that
That's right.
time interval, and you want to estimate the states. And so you do it in forward time, but once you arrive at the end of the time interval, you could go backwards.
Okay.
Use this information so that you use a collection of observation over that whole interval to estimate the collection of states over that whole interval.
Right.
Of course, it's for other applications, but
That could be. I don't understand 90%. I mean, 100% what you're saying, but I think it could be done for other applications, right? So if you want only to have a decision variable that you dispatch and things happen, that's a different story. You don't care what's happening in the past. But for monitoring reasons, or if you have a fixed time step, and then you could go back, and yeah, you could do that. You could use even instead of in fact the Taylor expansions over here is like a forward error method. You could use more complicated things like Runge-Kutta to do a much better prediction of how things works. But yeah, you need much more information in the past.
Did you try to have an approximation of the Hessian rather than to have a real one?
Of what?
Hessian. So do you try to have
okay.
an approximation to aspiration, or I don't know
Right.
what, or some kind of?
Yes, we did that.
Then
Yeah, I did not include it there, but the error, then the asymptotical error would depend linearly on the sampling period times the error, the maximal error you do on the gradient, on the Hessian. So you could approximate it if you have a bounded error between your Hessian and the approximation that you have, and then modulo technical details, you can arrive at the end saying that the error depends linearly on the sampling period times error on your Hessian. So it's possible. It just degrades what you have. It degrades the error, but you can do that. Then the question is whether then this method would work better than the other method at fixed computational cost, right? Is the error that you commit enough to justify the fact that you have to run now more prediction, or that depends. But to get back to you again, instead of, so in a Kalman filter you would need the Hessian, right, the covariance matrices, and you need to invert them. Here we don't invert them, so that's really the pros. Okay, I guess.
So we have no more questions. Let's thank the speaker again.